to week 17 of Pure Maths 3 maintenance. We're heading towards the exams. We're getting ourselves ready by reviewing topics that we've already covered in class. The first question is from the algebra section of the course. We've got, this is where we're dealing with modulus. So the way to solve these ones, we've got a modulus on both sides. So I like to just square both sides in this kind of situation. So I'm going to square that. And then I'm going to set it as equal, first off, to 3 squared, which is obviously 9, into 2x plus 1 all squared. And this is going to give me 4x squared minus 20x plus 25. And then it'll be equal to 9 into 4x squared plus 4x plus 1. Now what happens there? I guess we can expand the bracket on the right hand side there. So we get 4x squared minus 20x plus 25 is equal to 36x squared plus 36x plus 9. Now I'm going to bring everything across to one side, and I'll get 32x plus 56x minus 16. And probably at this point I'm going to divide by 8, because 8 goes into all of those. So I'll get, oh, that should be an x squared there. I get 4x squared plus 8x. Oh, sorry, 7x. I'm dividing by 8. 7x. And then I'm going to go minus 2 equals 0. And I'm going to factorize that, so I get 4x minus 1 into x plus 2 equals 0. And this is going to give me two results. X equals 1/4 or negative 2. Now those are the roots. That's why I did equals to start off with. So I found the roots of the equation. Now I move everything across to one side. So I should have in this point here, let's just think about this. At this point here, I would have had a greater than sign, because I moved everything across. So I should have less than here. So if I look at my roots, and my roots are at, I've got one here at, say, 1/4, and one here at minus 2. There, you're looking at this part here, which is where 0 is greater than what we've got. So I would write that, and my final answer is minus 2 is less than x is less than or equal to minus 1/4. And I'll be done with that. And this brings us to the second question, a log and exponential functions question. We're going to use some substitution to solve the equation and give our answer to 3 significant figures. So what I'd first do is I'm going to say, well, it's u plus, and then u 3 to the 2x is equal to 3 to the x times 3 to the x, isn't it? Because you add the indices. So we can say u squared equals, and then this must be u cubed, I guess. Now, what I would probably do, what would I do? I would probably factorize first, like this. Then I would divide both sides to get this. And then probably at this point I would bring everything across to one side and use my quadratic formula. So u will equal to minus 1 using the quadratic formula into minus 1 all squared minus 4 times 1 times negative 1. And this should be all over 2 times 1. And I end up with a couple of answers here. I get 1 plus or minus square root 5 all over 2. And what this means is 3 to the power of x equals 1 plus or minus the square root of 5 all over 2. Now, actually, if you think about it, 3 to the x cannot equal this minus value. It cannot equal this one, so we can ignore that. Because if you think about a 3 to the x function, okay, you're never going to get a negative value for it. So we can just change this over to a plus here. That's the only solution that we're going to have. And then at this point, I would just use log. So I'd go log base 3 of 3x, 3 to the x, should be equal to log base 3 of this function here, 1 plus square root 5 over 2. And so we get x is equal to, now when we plug this into the calculator, I'm getting 0.438, and that's to the 3 significant figures that were required. Now, moving on to our trigonometry question for the week. The angles of theta and phi lie between 0 degrees and 180 degrees and are such that tan theta minus phi equals to 3 and tan theta plus tan phi is equal to 1, and we've got to find possible values. Okay, this looks interesting. I might need a bit more room for this one, so I'm just going to actually shove everything down a wee bit. Can I not do that? It doesn't want to do what it's told. Okay, we'll just try and make do. I don't know what I'm doing with this program. Okay. Clearly. Okay, well, the first one I'm going to look at is this one here, which I'm going to use the addition rules for this. So, what will that be? We can rewrite it, and you get the formula sheet for this. So, I'm going to rewrite it as tan theta minus tan phi all over 1 plus tan theta tan phi equals 3. And I can rewrite that as tan theta minus tan phi equals 3, because I'm timesing both sides by the denominator, so I get 3 minus 3 tan theta tan phi. So that's one equation. The other equation that I can think of is this tan theta. So I'm going to go, what is tan phi equal to? So I'm now looking at the green highlighter here, this one. Okay, now we can say tan phi is equal to 1 minus tan theta. And we can do the substitution at this point. So I'm going to substitute this into every case of tan phi. So we get tan theta minus 1 minus tan theta. Use those brackets to make sure you're thinking carefully about how the substitution is going to go. And then this will be 1 minus tan theta. Okay, so let's expand this. So we get tan theta minus 1 plus tan theta equals 3 minus 3 tan theta. I'm expanding this second bracket plus 3 tan squared theta. Is that right? I think so. Let me just check that I've done that right. I think so. So at this point, what I'm going to do is bring everything across to the right hand side. So I should get 0 equals, and then we've got 3 tan squared theta minus tan theta, and 3 plus, is it 4? Plus 4. I guess we can factorize at this point. So I get 3 tan theta. Tan theta here. And if we're going to get minus 1, so I guess 3 plus 1 over here. We have the minus 4 here. Does that work? Yeah, I think so. So we get tan theta is equal to 4/3 or minus 1. Go over to here, switch colors as we move on to find what this is. Now we can apply since we can apply this formula here. So if you want to know what, find the possible values of theta and phi. Okay, so I guess we can find, maybe we'll find theta at first. So theta is equal to the inverse tan of 4/3, or inverse tan of -1. So let me just quickly chuck those into the old calculator. So I'm getting like 53.1. And it's 10, -1. And so that's between 180, so that, I think that's 135, isn't it? Yeah. 135 degrees. Now what we're going to do is we're going to just simply apply this jolly this formula here in the pink underline. So tan phi is 1 minus tan theta. So we know what the tan theta values are here. So tan phi equals 1 minus 4/3, or 1 minus 1. So tan phi equals 1 minus 4/3, which is like a negative 7/3, isn't it? And then, oh sorry, what the heck, minus 1/3, wake up. -1, or 2, and then so phi, we do the inverse tan of those. So inverse tan of -1/3, that gives us a -18, but we just add 180 to it, so we get equals 161.6, and for the 2, inverse tan of 2 is 63.4. Those are our answers for this. So that didn't prove to be too difficult. Okay, so the differentiation question for the week. So we've got this rather annoying looking question. You can see we've got this and this multiplied by each other, so we're using the product rule. And just to refresh your memory, the product rule, we go dy dx is equal to u times dv dx plus v times du dx. Okay, and we just define u, I guess we'll do is e to the minus 2x. So dy dx here is going to be equal to e to the minus 2x. So this is u. And then we're timesing it by, well, when we do, so v is going to be this one here. Okay, now when we differentiate tan x, we get sec squared x, so it's that one, plus, now we do v, which is tan x, into du dx, so we've got to differentiate the e to the minus 2x, and that would be minus 2e to the minus 2x. And they're wanting us to write it in this kind of form here. We've got tan x, so sec squared x we know is using our rules, our identities. So sec squared x is 1 plus tan x. So I could rewrite this. And remember, those identities are given in your formula sheet. So 1 plus tan squared x plus tan x into minus 2e to the minus 2x. So then next line, you can actually factorize this e to the minus 2x out. And you've got 1 plus tan squared x minus 2 tan x if you factorize. So you can see, hopefully I'm taking this minus 2 and just popping it in front of the x. And the one that I'm factorizing out is this here. I'm factorizing that out from both of them to get to here. Hope that makes sense. Okay. Alrighty. Now, what do we need to do? Now, if you look at this is like a quadratic equation, isn't it? Yes. So we could write it like tan x minus 1 all squared. Okay, which would give us tan squared x minus 2 tan x plus 1, which is what we've got. So that's exactly what we want. They've written it slightly differently, so maybe we should write it the same kind of way they want. Minus 1 plus tan x all squared. There we go. Okay, well, we've done what they wanted us to do. Now we've got to explain why the gradient of the curve is never negative. Okay. Well, first of all, we go back and look at our domain. So we're putting all of this stuff in here. Okay. And hopefully you'll notice that whatever you get in here becomes positive because you've got this square. So first thing is minus 1 plus tan x squared is always positive, and e to the minus 2x is always positive, and a positive times a positive is a positive. If you're thinking about e to the negative 2x, you might be thinking, well, what does that look like? Isn't it sort of like this, isn't it? Alright. Find the gradient of x for which, find the value of x for which the gradient is least. Well, lowest gradient. How do we get the lowest gradient? Okay, well, maybe if we look back to our gradient function, this is the gradient function. How do we get the lowest value? Well, we're going to get the lowest value when this bracket here equals to 0. So therefore when tan x equals 1, and so x should be equal to, and you go inverse tan, or I mean this is one that we should have learned off by heart, isn't it? It's pi over 4. Okie dokie. Number 2, 1. I'm not sure what that's doing like that, but anyway. What are we trying to achieve here? The diagram shows the curve of blah, and we've got this. We've got to find the exact value of the x coordinate at the maximum point. Okay, so it looks like we've got to differentiate. Now this is using the quotient rule. The quotient rule. Now the quotient rule is we're going to have where we've got y equals u over v. We therefore will differentiate and we'll get v du dx minus u dv dx all over v squared. And in this case, you've got your u is this one, and your v is the pink one there. So here we go. We get v, so we get 1 plus, so we want to find the minimum point. So dy dx is equal to 1 plus x cubed, bracket 2x, minus x squared into 3x squared all over 1 plus x cubed, and that is all squared. Now, what does this give us? Well, we get 1 plus 2x to the power of 4 minus 3x to the power of 4 all over 1 plus x cubed, and that is all to the power of 2. Now at this point we can simplify that to 1 minus x to the power of 4, it's a bit messy, x to the power of 4 all over 1 plus x cubed squared. Alright, well, that's good. Now what are we going to do? We need to find the maximum point. So maximum point m, whoops, daisy. Now the maximum point m occurs when the gradient function equals 0. So for it to equal 0, your numerator, the numerator has to equal to 0. So we're going to set this equal to 0. So we go I may have made a... Oh, I should have got a 2x here. I was just looking back at this first thing here, and I should have a bracket shown here. So I'm thinking, yeah, sorry guys, that should be a 2x here, shouldn't it? And so this should be a 2x here. I'm just, because I did this earlier this morning, and as I'm doing it on the screen, I'm getting a different answer from what I was doing this morning. So yeah, so we're going to set 2x minus x to the 4, and we set this equal to 0. Now, I'd probably go x bracket 2 minus x cubed equals 0. And so we can get x is equal to 0. So there should be a minimum point or maximum point there, which you can kind of see them probably is. Or the other one is x cubed equals 2. So x is equal to the cube root of 2, which I think is the one that we want. And that's all we need there. So that's this one here. Okie dokie. Now the next one is an integration question. How are we going? Oh, yeah, we're doing well. It's an integration question. And what do we know? Got x squared. Okay, so it's the same thing that we're integrating, and we're trying to find the shaded region. So it looks like we're integrating the whole thing between 1 and p. So I guess we could write it like this. X squared over 1 plus x cubed. Now I'm noticing that this is one of those ones that the top looks like it's some kind of derivative of the bottom. So remember, when you have something like this, you're going to be doing ln fx. Okay, so in this case it looks to me like we need to go 1/3 ln yeah, because it would be 3x squared on top, so we want 1/3 to get rid of the 3, so ln, and then would be 1 plus x cubed, and then we put in our limits. Now we're trying to calculate the value of p for which the area R is equal to 1, so we're going to set this equal to 1. So we take our upper limit. We're going to go 1/3 ln 1 plus p cubed minus 1/3 ln 1 plus 1 cubed. And so we get 1/3 ln 1 plus p cubed. And this is, sorry, and this is meant to be equal to 1 minus 1/3 ln 2 equals 1. Now what I would do at this point is I'd probably bring everything across to the other side. So no, maybe I'll times first. I'll go ln 1 plus p cubed minus ln 2 equals 3. Then I'll bring so I'll leave ln 1 plus p cubed on the left hand side, and then I'll go 3 plus ln 2 over here. And then probably I would go, because I'm trying to find p, so I'm going to go ln 1 plus 1 plus p cubed, and then I'll make that 3 into ln base ln of e to the 3, right? Because that's 3 plus ln 2, and then we can rewrite it as ln 1 plus p cubed equals ln 2. Well, bother. Ln 2 to the e cubed. All right. I think that's what I want to do. Oh, ln base. Yeah, I think that's what I want to do. And then I can remove the ln, so yeah, 1 plus p cubed equals 2e to the 3. So p cubed equals 2e to the 3 minus 1. So p cubed equals the, p equals the cube root of 2e to the 3 minus 1. Now, what the heck does this give us? 2e cubed minus 1, and then we take the cube root of that, and I'm getting 3.40. 3.40, and that's to 3SF. So that seems to be right. Okay, next one. What have we got? The equation blah 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 has one real root denoted by alpha, and we've got to find by calculation the pair of consecutive integers between which alpha lies. Okay. Well, it doesn't really give you any hints as to where to start, so I'm just going to start with x equals 1. So when x equals 1, we get 1 minus 1 minus 6, we get minus 8. Okay, when x is equal to 2, we get 8 minus 4, which is 4 minus 6, which is minus 2. It looks like we're getting closer. X equals 3, we get 3 cubed, which is 8. 27 minus 9 minus 16, so we get positive 12. So that means that root lies between 2 and 3. And we've got to show that if a sequence of values given by is given by this iterative formula. So we're going to look at this formula here, and we're going to try and derive something like this. Okay. How could we do that? So I think we probably want to move the 6 across first. So we go x cubed minus x squared equals 6. Then we divide, or factorize perhaps, like this. And then you can get the x squared minus x equals 6 over x, which is kind of what we need to do. Yeah, now we're there. X squared equals, and we put x plus 6 over x. So you see we've got this bit here. And now we can square root both sides. So x equals the square root of x plus 6 over x. And we can therefore say the iterative formula x n plus 1 equals square root xn plus 6 over xn. And that would be that. Okay, and then it's a very easy matter to use that. Now the last question for today is a vectors question. The points A, B, and C have position vectors relative to the origin given by OA is 1, 2, 0, OB is 3, 0, 1, OC is 1, 1, 4, and we've got to find the vector equation for the line passing through A and B. Okay, so the first thing is we're going to find AB. Now AB is equal to, we're starting at A and ending at B. So you want to go, maybe I'll write this in vectors first. So I want to go AO, and then I want to go OB. In other words, AO, which is the negative of OA, so it's going to be negative 1, negative 2, 0, plus OB, which is 3, 0, and 1. And this will give us vector 2, negative 2, 1. Okay, so that's the directional part of the line. And then we've just got to have a point on the line, which of course is point A. So we can, or B, I'm going to write it with A. So I'm going to go R equals, which is how we write a line, R equals point on the line, 1, 2, 0, plus the directional vector times a times mu, so because depending on how far along the line you are, you have that value there. So it's going to be 2 minus 2, 1 with the directional vector. And that's it. So that's a nice easy one to finish off on. Probably not an exam question, probably just something I pulled out of a textbook. Alright, well, I hope that makes sense, team. Let me know if you've got any questions or if I've made any errors. Alright, take care. Bye.